So hi again, everyone. Thanks for joining us again. This morning we had a Git session. The session today is about a different topic, but then it will be complementary. We'll also see another Git command we haven't discussed today in this session. And we'll also have an exercise after about 30 minutes of discussing scripts. We'll have an exercise that combines the knowledge of Git with RMG scripts, just for fun, but I would love to have an hour of my time just devoted to learning that stuff. So if you have an hour and you're already here with us, remotely or here, take the exercise seriously so you can see that you really master both Git and how to use RMG scripts. Afterwards, we'll have some concluding remarks and we'll conclude our workshop this week. So we're starting with scripts in the context of RMG. RMG has many features. RMG has many modules, many functions that it uses while it does its own purpose of generating a model. But for different purposes, we might want to use some of its already well-defined functions or methods or classes for different purposes. For example, just checking out what are all possible reactions between two reactants or one unimolecular reaction. So RMG does that anyway. It needs to know all the possible reactions. It will rate them, rank them by rate, and will incorporate into the core species which are important. But wait, stop. I didn't want to do all that. All I want to do is just know which reactions could occur potentially between two reactants I care about. RMG does that, but it doesn't output it when you run RMG organically. So we can tweak it around. We can use its methods and functions to do what we care about. You can always do that. You don't need Past. If you know the API, if you know how to call these functions, and you can look at our documentation as we show in the workshop, you can do that from scratch and build your own script. But since there are things which we do repetitively and we need as model generators, as human model generators, we need to do them quite a lot. So we already made scripts that you can just take from the shelf and use. So scripts in RMG, we have two groups. We have scripts in the RMG-Py repository under RMG-Py slash script, and under the RMG-database repository. We have several of these. Let's look into them soon and discuss several which might be more relevant. So why we have scripts? As we said, we want to run an analysis, so we want to gather more information about something we care about, which isn't RMG's primary goal, but we're using RMG's methods outside of an RMG run. How we do it? Using the command line, or you can SSH a server, but we're using the command line usually on our personal computers. You first activate the RMG environment. So whatever you do, you already defined the Anaconda environment with all the packages. Whatever you'll be doing and using different packages, they'll already be there in your environment, and you'll be able to use them. So first, you activate your environment. On Linux, you need to do source activate RMG-NV. You can shorten source for a period. So period or dot space activate RMG environment. Then you call the script. So first you type Python, so you know which interpreter to use for the script. So Python, the name or the full path to the script, a file name or a relative path, and some parameters. Each script requires different parameters, and we can see soon an example. On our documentation online, in our documentation, there's a section of standalone modules. So it's a different name, but it's the same thing. These are our scripts, the standalone modules that you can use. So you can look them up on our documentation. Not all of them are there, but large or many of the important ones are documented there, and you can see how to use them and what they do. We'll also discuss some of them here. So here's an example. Let's say you want to import a ChemKin library. So you have a ChemKin file with a well-defined dictionary. RMG needs to know the structure of each species, not just the label. It needs to know the actual 2D structure of the molecule. So if you have a ChemKin file and a dictionary in RMG's language, you can import it and use it as a library when you generate further models, a kinetic and a thermal library. So here's just an example of how you would use it. You would write, after activating the RMG environment, Python, call the script, or give the full or relative path if it's not in the folder you're currently running at. You need to give the ChemKin file name and path, the dictionary path and file name, and a name that will be used for the library. So that's just an example of how we do that, and that's taken from our documentation.
What's the -H with the bracket?
You can type -H and it will give you help. So it will just speed out these directions. Is that correct?
Yes.
Yeah.
Okay.
So
And with the brackets like that?
And so the brackets say that optional.
Okay.
And then if you do that, it won't read, I guess it won't read these parameters. It will just speed out help or the documentation about that particular script. So let's go over the example word by word to understand what we're doing. So here's a more specific example. Before we just had parameter names. I can, after activating the environment, I can type Python, then give the script name. So here it is. Python, the script name, and the path to the ChemKin file. If it's all in the same folder, I don't need to specify the actual path. The path to the species dictionary, and then just give a new name for the library. Here's new lib. So here you have everything in one line. And so that's how we would call such a script. Let's look at our scripts in the different repositories, RMG-Py and RMG-database. Let's start with RMG-Py. Some of them are outdated that we don't use a lot. For example, converting from very old formats to new formats. But here are some which are relevant. For example, diff models. If you want to see comparison between two different models, whether generated by RMG or not. And Max showed such an example on the website. It does that as well. So that's a very useful script. Let's say you generated the model, perfect, run a sensitivity analysis, you ran a sensitivity analysis, and you did change a parameter that your observable was sensitive to, and you have a new model. We'd like to see the differences, and that's a good method to do that. Generate reactions, as we just said, to generate all possible reactions that RMG could think about for given reactants. Merge models, if we have several RMG models and we'd like to merge them into one, there are some overlaps, there is some new information in each one of them, could be, so that's a method that will do that. Sensitivity analysis, we already showed in the sensitivity analysis session yesterday how to run sensitivity analysis in RMG. You could also just call the sensitivity analysis script, feed it an RMG output, an RMG model. I think even any ChemKin model, any model, you might need a dictionary here, and it will output the sensitivities and will calculate it for you. And for a constant temperature and isobaric reactor, that's what RMG currently simulates. Another one, standardized model species names. So it will change the name. Sometimes it doesn't fit to if you're using older ChemKin software. Thermal estimator, the same as generate reactions. If you'd like to just estimate thermal for a bunch of species, so you can give RMG access to certain libraries and of course repetitivity or machine learning, and it will estimate thermal for you. So these are all scripts in RMG-Py. They utilize RMG-Py's methods and and functionality. Other scripts are related to RMG-database, as you can see here. Let's see what we can elaborate on. So events Polanyi, you can generate a plot according to the events Polanyi equation. Export library to Kenkin, so that will be the reverse of what we discussed previously. You already have libraries in RMG. Let's say you want an entire library as a Kenkin file, not in the format it is in our database. So this script will do that for you. Import Kenkin as libraries, import Kenkin library. How is that different than the script we showed before?
The same one.
The same one? Right. It's just duplicated in the repositories. Right. So these are principally the scripts that are available, and we'll give some examples. Any questions so far? So that's all for the very short presentation, and we'll resume the different machine. Okay. So we'll give examples of running two scripts. Purposely, I didn't make too many preparations of preparing the input files and everything in place so we can just press a button and get the results. I wanted to create it with you to see if you have a purpose that you want to achieve with scripts. How would you go about doing that from scratch? Let's start from the diff models script. Although you saw it on the website, it's also useful to just run it locally and have everything on saved on your drive. And it's a nice example of how to run scripts. What I did prepare are, of course, two mechanisms that we want to compare. Otherwise, it would have taken a long time. So here they are. We have model 1 and a dictionary, model 2 and a dictionary. Let's just see what's inside each of the files. And just for model 1, for example, here's a Kenkin file. We have elements, we have species, and then thermodata, and eventually some reactions. Both are for a sulfur system. Here's the dictionary. The dictionary relates each of the labels in the Kenkin file to an adjacency list in RMG. So we know the exact structure. Species isn't just a name, just a label. We have physical properties that we can derive, some physical properties from two-dimensional representation of the species. So what do? We need to first have the actual script. Remember, we have several parts, so what we were going to type in a terminal, Python, the script name, and then some parameters. Here the parameters will be this file, the models we're going to compare. So you can either give an absolute path to where the script is located, or just copy the script, and that's what I like to do. Let's just take physically the script. It will be under RMG-Py. If you don't have the developer version, if you have binaries, you can copy it from GitHub, just download it. And so RMG-Py script. And here we have the diff models. Show the difference between two models. Here it is. Great, let's run it. I'll first activate my environment. Great, you can see that it's activated. Now we'll call Python, but then wait, I'm not entirely certain of the order in which I should put the parameters in what I'm going to write. So let's open the actual script. Or we can type diff models dash H. I think that would also work. And it should output something like that, and it should give us an example of how to run it. So you should write Python, the name of the script, and then the parameters will be Chemkin1, species dictionary 1, Chemkin2, species dictionary 2, which are our models we're going to compare. So we'll do exactly that. Python diff models, model 1 input, then model 1 dictionary. I'm pressing tab so it auto completes me if there's only one choice. Otherwise it will show me the choices. Then the second model, model 2 input, model 2 dictionary. That's it. Let's see. Compares these two models, generates a bunch of files here. Principally what we have is then an output file in an HTML form and species images, so we can visualize it, save in these folders. We care about the HTML file. Let's open it and see. Again, Max already showed a similar example on the website. The website can do that for you, not running from the terminal. And we see for the two models, it will always say model 1 and model 2, although I chose the same names for my model. I also called it model 1 and model 2. That's like just a coincidence. I could have named my models anything. It always says model 1 and model 2. So you should remember which one you fed to the script as model 1 in the parameters in the command line, and which model was model number 2. You can also show the thermal details if you like. In blue, we have species with identical thermal, and then in red, we have something different. For example, H2S have different thermal values. That's on purpose, just to show a difference. These two models have different reactions, but the thermal is the same. So on purpose, I just modified one of them. I added a comment that it's taken from modified library. It doesn't exist. I just named it differently in the Chemkin file, which has annotation, and gave it some arbitrary parameters, just to show that that script captures different thermal. Other species really have identical thermal. We can browse down until we get to reactions. So here it is. First, we have unique species. So species only one of the model sees. So model number 1 has these unique species. Model number 2 has these unique species, and we can see the thermal data for them. Then reactions. So again, several options. You can only show differences in H abstraction and so on. So you can check these boxes and show specific differences. You can check kinetics. It will actually show you the kinetics predicted, and you can see what are the differences in kinetics. So again, blue means all these reactions are identical in kinetics. Let's find some which aren't. So I can search. All right, here's one. With different kinetics, very different as we can see. Why is it so different? One is fitted from reverse, another one isn't. So maybe we have a better training reaction. I don't know. It's been a while since I developed that model. I just took it as an example. But for you as model developer, once you see a difference, you should study and understand where it came from. Particularly when it comes from a pressure-dependent network, it's hard to tell just by looking at that script. So what I would do is go to model 1, where I actually generated it. There's a folder of fitted files. There's network number 7. I'll go to network number 136. I'll see the differences. If it's hard to see by eye, the networks might be large. I would have run them by Arcane. It generates a nice PDF file with the actual network, so you can at least visualize the energies and which species were added or removed. So that's a way to see differences in specific networks. But you don't have to guess which network relates to which. You can see it's exactly network number 7 and 136 in each of the models. All right, so that's the idea here for model comparison for that script. Any questions before we move on? All right. A second example I'd like to show is generate reactions. So let's do it together. We'd like to generate reactions for two species. We'll decide on them as we go. And I'd like to do it with you from scratch. So how do I start? I need to first grab the actual script. So I'll go to script and generate reactions. A very useful script. I'm going to copy it. I don't have to copy. I can also provide a full path, but I think it's easier. And then we'll grab an input file. For generating reactions, you need to provide an RMG, an actual RMG input file. It won't read all the sections, but it does need to know which species and some other options that you can specify in the RMG input file. But it won't relate to the conditions, for example, and your reactor that you define in your input file, because it just generates reactions. It won't determine their importance, so it doesn't need to know the actual conditions. So we need an input file, just something. So a good place to go is RMG's example. RMG. We can just choose an example, it doesn't matter. Let's take ethane oxidation, we took it once. I think it's a convenient input file. Let's see what we want to add to it. So take a while if you want to generate reactions, and if you know there are libraries which matter to you, you can add them here, and that's important because it will affect the output of the script. It will generate reactions considering these libraries or not if you don't specify. So that's an important attribute. Other than that, you should specify the species you would like to generate reactions between. And RMG will consider unimolecular reactions and bimolecular reactions for what you specify. And you can specify an entire list of the number doesn't matter, but as many species as you like. For each one, RMG will show you all unimolecular reactions, and possibly if there are bimolecular reactions of the same species, for example, ethane plus ethane, it won't happen here, but if instead of ethane we have ethyl radical, so they could recombine. We'll rename it reacting with oxygen. Let's take that. The input file should be valid, but again, the script won't look at these conditions anyway. Or termination time, right? It doesn't run a model. We have pressure dependence on, so that's great. The reactions will have pressure dependent characteristics, and the values you put here do matter because they affect the Chebyshev fitting. One last thing that you should know when running generate reactions is that in options, you need to save the edge. You need to save the edge species. It makes sense if you think about it. You're not really running RMG now. You're just generating reactions. When RMG generates reactions, it populates the edge. Then if something's important, it will incorporate it into the core. But we're not doing that entire process. We're just populating some edge, and that's the result. That's our output. So if you're not saving the edge, you might not see the output. So we'd like to save the edge. If you don't know the keyword for that, that's okay. Just look it up, either on our documentation or a very nice place to look up for syntax is the RMG commented input file or commented example. So here's an input file with all the options that exist. As you see, it's very verbose with lots of examples. I care about options, so model, options, here are options. And I'd like to see save edge species. I'm going to copy it for the exact syntax, and I'll change it to true instead of false. So that's the only thing really you need to have be knowledge of for that particular script. It also makes sense, but it might take a while for that particular script. If you have it on false, you might be wondering where your output is. That's it. We can now run our script. How do we run it? So here it is. Let's make sure I save it in the right place, right? We have saved edge species. It's the right input file. Generate reactions. Principally, you call generate reactions and the input file, and that's what is being said here in the directions. Should be straightforward. Let's try. I'll cd into that directory. Python, I already have my environment activated, so Python, generate reactions input file. It loads the database. We didn't give it much libraries, but it still trains the kinetic families using the training reactions. So here it is, adding rate rules from training sets in kinetic families. That might take 30 seconds or something like that. Other than that, we'll see an output like a normal RMG run. We'll see it populating reactions, calculating pressure-dependent kinetics, but that's it. And then it will terminate, and we'll have our result of all the reactions between ethyl radical and oxygen, including self-reactions or unimolecular reactions. It should have done it so far by now. I guess it's my computer's fault, which isn't as fast as we would like it to be. All right, here we go. We already discussed these warnings. At first, we didn't use thermal libraries to include certain species which aren't necessarily in your input file. They're in the training reactions, so they're somewhere when RMG made the training reactions, trained to the families, and it outputs warnings where, for example, CP infinite is too high, or CP high is higher than CP infinite. And here we go, generating reactions, calculating pressure-dependent reactions for just arbitrary species we chose, and we're terminated. So mainly most of the time was on loading the database. You can see that the core has 6 species. Why 6 species? We have 2 that we cared about. We have some inerts, and we can see why we have 6 species. Let's see what else we have in our core. But 0 reactions, so no reactions made it to the core, and our results should be here in the edge. So that's another indicator that you should save your edge. Let's see. The output would be first here in HTML files. You can just open them as we did before. You can also look at the Chem folder. Chem annotated would be our core. Let's see just which species we have here. We have a bunch of species, I see. Thermal for all of them, and we do have rates. So we do have it in the core. I'm still a bit confused because sometimes I don't get them in the core. RMG said we don't have species in the core, but that's okay. We didn't really run an RMG job. All we wanted is to get some rates, and I see that we do get it in the core. That's great. I warned twice, and I said we need to save the edge out of experience because often I don't get the reactions in the core. Anyway, you will get them somewhere, either edge or core. So here we have them in the core, and let's take a look. So ethyl reacting with ethyl radical. Here again, ethyl and ethyl are reacting, H obstruction, and that's disproportionation, and so on. We can take a look at the HTML output, which is more clear. So here are our species. We have some inerts that RMG adds by default. If you're using VDEP as we did, you have to have at least 1 inert And we have several here, and here are our reactants, and lots of products RMG predicted possible, and you can visualize the reactions. Not that many relevant reactions, which is great if you just want to analyze the reactions being generated for several species. You can also do that on the website, of course, right? There's the generate reaction or kinetics section of the website, but here it also outputs your a Kentin file for you if you want to further process it, which we often do. So it's useful in that sense. And before we move on, any questions so far? Great, and work to explore. Next thing I would like to show you are our IPython notebooks using Jupyter. If you're unfamiliar with these terms, so you'll see it right now, Jupyter is a platform that comes with Anaconda. You just installed Python with Anaconda, that's how you have RMG. So you have it, you already have Jupyter notebooks installed on your laptop, on your machine. Let's see how you call them. So choose just any folder, and you call Jupyter notebooks by just typing Jupyter with a Y, Jupyter, like Python, and notebooks, or notebook, Jupyter notebook, in a certain folder. It will open a browser window for that certain folder, and you can see everything inside. So let's go to RMG-Py, and under RMG-Py we have another folder called IPython. It's another name we use for Jupyter notebooks, IPython. Principally, it's a Python interface. You can write Python code and execute it in cells in the browser. It's convenient. And we can see, I'll show you one example of, again, generate reactions for a different chemistry with already pre-calculated results. So principally, once you load that up, you get a nice explanation, and you can run each of these cells individually. It's very helpful as developers. You can have parameters calculated here, you don't need to recalculate them, and you can continue working in the same namespace in a different cell. And so you can run them, you can just click run or run all. That will restart everything, clear the output, and run everything. And here we again call the generate reactions script for a certain molecule. Let's see what it outputs. Here it is. And it outputs the same thing graphically, and it shows you that was the initial molecule we had in mind. It shows you all possible reactions and where it's taking from. I think it's even a bit more convenient than just running the script and looking at the HTML output as we did before. But if you need the Kentin output, then run the script in the command line as we just did. This just shows you a nice visualization and explanation of where the reactions come from. And you can see the averages that RMG takes here, for example. Look at all these averages. So it's important to note. So you can see it's average of many averages to come up with a rate. It might be the best rate in literature, but it's definitely not a perfect estimation for a rate. And here it is right here. So that was just an introduction. We definitely didn't go through everything, but I think it gave us some tools of understanding how to work with scripts, what they are, and what are IPython notebooks. Just a taste, and you can continue exploring on your own and work in that environment as well. It's very convenient.
What is the difference between IPython and Jupyter?
Sorry, what is?
The difference between IPython and Jupyter?
For me, it's the same. IPython and Jupyter notebooks, yes, ma'am.
Yeah, so IPython was the original interactive Python, and then Jupyter notebooks came along and sort of integrated it into the web interface.
And so we have a directory called IPython, but it's actually full of Jupyter notebooks. Right.
Yeah, so there's a mix in, in naming. So,
all right.
And you initiate it by typing Jupyter Notebook, as we saw, but the folder is called IPython. For us, it's the same, but I understand it's a bit confusing. All right. So that was the first part of scripts. Before we start our exercise, there's one thing I think I owe you from the Git session before. I think the Git session helped all of us to have a good understanding of the way Git thinks, the workflow, branches, what staging is, what committing is, and now you can pretty much understand any new Git command if you take a while to think about it, because you already have a good grasp of it, of Git essentially. What I haven't showed you is how to work with remote repositories. So how to push things to GitHub or pull things from GitHub, which is A, important, and B, we'll need it for the exercise today, just to practice. So that's it. The connection failed because I just closed the terminal. I'll close everything but the WebEx and screen share. So first I'll go to GitHub and load up my user. We'll go to repositories, and I'd like to create a new repository. I'll create the same repository locally, and I'll try to push from my computer online, and we'll see that we can see the changes online as well. So I go to repositories, click new. You'll need to do that soon as well for the exercise. So under my username in GitHub, the repository name will be Git demo, and you can call it whatever you want. It's a public repository, and I can create it. Right, here it is. I can set up a README file and other settings. Let's just advance. Right. So it shows that because there is nothing in the repository. If there was something, it would have shown something similar to what you see when you load up RMG. But currently there is nothing there. So we call the repository Git demo. I'll open a folder under code. I already have Git demo. Let's delete it and make a new one. Let's create a new document here. All right. A very simple change. Let's add it and commit it, so you already know everything by heart, right? Git status. We'll see. Of course, nothing here, nothing to report because I haven't what? Initialized. My bad. Let's initialize it. Let's say that, let's tell Git that this is our repository. It's not enough to just open a folder. So let's tell Git it's a repository.
Maybe you should just continue working with the
previous one? We could do that. We could do that. But yeah, you're right. We could have done that, but that'd be good. Let's use this one. So git init for initializing new repository. Git status. Here's our status. There's an untracked file. Git add. We're adding it. Git commit -m. Git log, here's our commit. I would like to push it. So push it where? I should tell Git about my online repository, and they should communicate. So we define that as our remote repository. So typing Git remote will tell us what Git thinks about our remote repositories, which currently is nothing. So we need to add our remote repository so Git can communicate with the local repository, between the local repository and the online one. So Git remote add, let's give it a name, origin for example. You can give it any name you'd like. And I'll just copy the address here, the web address of my repository under my username and the repository name. And I'll paste it here. I'll type git remote again, like typing git branch to see what branches I have. So I'm seeing which remote Git is aware of. So it's aware of origin, it's aware of origin. What is origin? I don't know. So let's type git remote -v for verbose to have more details, and I can see, all right, origin sits on my username on GitHub, and it's the Git demo repository. Now I can push there. So let's do that. I want my code, my single commit, to be pushed to GitHub. So git push origin master. Git push will tell it to push my current code, my current branch. If the branch name is the same, so I'm currently on master, it will push it to origin, to the equivalent master branch. And my username, my password on GitHub, which you already have an account, so you have your password. All right. And off we go. Let's look online on our repository. We can refresh. Great, we have something. Here it is. Here is our branch, master branch, and here's our file. We just pushed it. We can also fetch and pull from an online repository. Someone just updated RMG. On the RMG documentation, you can see exactly how to do that in Git, but let's do it together. I won't be pulling from Git demo because I'm already up to date on my machine, but we can go, for example, cd into RMG py. The commands here, which we won't be using for exercise, but these are complementary commands to Git push. First, Git needs to be aware of all the changes online, so we'll fetch the remote. What remote do I have? Let's see. Git remote -v. I have two remotes. One is called official, one is called origin. These are just labels that you can use. You can use whatever you want, but these are conventions. We use official and origin. We use that label just so we won't have to retype that entire address every time. But principally, the label just refers to that address. So official is the RMG version on the official RMG version, right? And origin is on my own account. So I'll try to fetch official. Let's see if there's anything new that my laptop isn't aware of. So git fetch official. Principally, if anyone pushed to RMG on GitHub and recently, and my laptop isn't aware of it, I haven't fetched in a while, now I will be aware of it. It won't change my files, it won't change my branches, it won't really update it. I'm just fetching all of the new branches that people added. So I see someone just added a new branch called parallel RMG reaction generator. All right, but nothing new on master. If there was something that was merged on master, I see my RMG version, my branch is up to date. If it wasn't, I could have just typed git pull from official, pull branch master. I can first verify that I am on the master branch. Actually, let's do that. Yes, I'm on master, so git pull, I'm pulling from official master. If there was anything new, you would have seen the commit being, a report of the commit being added. So that's the only thing I want to show that we didn't discuss in our Git session. And I think if there aren't any questions, let's start with an exercise that directs you both to use an RMG script and to deliberately make a merge conflict, resolve the merge conflict, and then push it to your own repositories we just did. So you have all the tools. We're here to help. If you need help with any specific Git command, you can always ask us. We can also write them on the whiteboard if you'd like, or you can use the cheat sheet in your virtual packet that we sent you, or just Google them, and we're here to help. So here's the exercise. I also printed it, so once we actually drill it, we'll do it at the end of the session and do everything here together, given that we have enough time. So if it's not on the screen, it's already also printed for you. If you're viewing us from remote, you can see in the screen share. And take your time, follow the instructions, and we're here to help. Try to actually take it as a serious drill to see that you understand and master Git and how to use an RMG script. So good luck, and let us know if you have questions. You can come speak. We want to first generate reactions. We already did it in the beginning of this present session, and we already also initialized the Git repository. We did all that in the current session. So I'm not initializing that repository. It's the same one we just had. I deleted that hello file we had. We'll commit that we deleted that file. That's okay. I'm opening the folder, the terminal, and let's just run the script. I need to activate my environment, of course. I have a shortcut to do that. You can just type source activate RMG environment, RMG env, or create your own shortcut. So here I think I'm generating possible reactions between ethyl radical and O2. The exercise wanted us to use OH. I think it's very similar. We'll just go with what we have here. And once that's done, we would like to commit all files. So we'll use git branch, git status, the toolbox we have to just figure out what just happened. So we'll use these commands, but then we'll stage them.
So first commit this.
Commit just the output files from that.
Yeah, it doesn't make a lot of sense.
Okay. That's what
Yes.
Okay.
Yeah, we're not pushing it into RMG.
And what are they going to have merge conflicts with?
So we're going to create the merge conflict in the exercise.
Okay.
We're going to, first we need to commit it, then we'll branch off, make a change in both branches, which is the same line but different changes, so that's a conflict.
Okay.
Then we'll resolve it, which is an excellent exercise in resolving, although the actual code behind it is meaningless.
Yeah, so not
It's not even a code.
No. Because that's when you're on. See, that doesn't do anything unless because you're on the branch. Yeah. So in theory.
So I think this file is actually different because this is
Right. Yeah. Exactly.
This is no longer there. This is taken out.
So new exercise should have the commit that includes the FOCM. In theory, if you do git merge.
All right, and we're done. We just generated it. Let's commit everything. So git branch just to see where we are. We're on master. Git status. There are many files that were just generated. Let's add them all. Git add all and git status. All files are now staged. Git commit -m. I generated it plus with O2. The exercise says OH. Whatever you did, that's great. I'm committing it all. Git status is clean. Let's branch off. Git branch. Great. Git branch. Let's call it FFCM. Git check out FFCM. You already know how to do that in one command. Git branch just to make sure where we are. And we're not rerunning the script. All we want to do is to add the FFCM1 kinetic library. And in parentheses, it says no need to really run the script, but you could. So FFCM1. In parentheses, there is a minus sign because we took out excited species. So just we want to note that it lacks some species from the original FFCM project. Here it is. I just added that. Next thing they want me to do, look at the differences. So git diff. Yes, there's a difference here. I can visualize it and I understand what's going on. And then commit. So git status. There is a modified file. Let's add it. Here it is. It's staged. I'm committing it. And let's check out master again. Return to the master branch and add a different library. So git check out master. We'll reload the file. FFCM isn't here. We can add now the exact name is GRI-MEC 3.0. Added and save. Let's commit the changes. So again, git diff to see what's changed. Git status to see the files, so we can see which files were changed and what changed in them. Git add. Git commit -m. All right, committed. Git log, we can see what we just committed. Now we would like to merge two branches, so git.
Okay, so what ended up happening?
So let's start with git branch, so we'll know which branches we have and make sure we are on master. Git merge FFCM would merge FFCM on master, but hey, wait, we have a conflict. So we need to resolve it first. Let's go to that file and see what the conflict is. Let's reload it. And I remind you, Git doesn't care how you resolve the conflict. All Git cares about is that a human looked at the file and said, that's okay. That's the way I want it to be. Git doesn't care about the code. You need to make sure that the content is what you want it to be. If you just get rid of these funny signs, Git will be happy. The question is whether you as programmers will be happy. So I'll get rid of these signs once I determine what I want to do. I want to keep FFCM. It's a more updated project than GRI, so I'm going to delete that, and that's the version I want to keep. I'm happy as a programmer. Git isn't happy because of these funny signs, so I'll just delete them, meaning that a human just took a look at it and said, that's the correct version. That's how I resolve the conflict, and that's what I want to keep. I just saved it. And remember we said a merge conflict, once you solve it, it's just like normal workflow. You just have a change in your workflow. You need to stage it and commit it, as we saw previously. So git status, here's our change. Git add input file. Git status again. It's now staged. And let's commit it. and we just added FFCM1 minus, right? Git log, and you can see the history of our branch. So we added GRI mech, we merged a different branch, there was a conflict, and we resolved it, and that's our commit. Merged, solving conflict will be shown as our regular commit, and that's what we did here. We added FFCM1. And now, after we carefully merged, and we did that, we would like to, and we solved the merge conflict, we need to create a respective repository online, which we did at the beginning of this session, and we'd like to push it, so let's push it. Where am I pushing? Official, origin, I'm all confused. So let's ask Git, what are my remotes here? Git remote, -v for verbose, it will tell me the exact address, otherwise it will just tell me that it's called origin. So I can see origin is indeed my user on GitHub, and it's a Git demo repository, and I want to push there. I'm on branch master, let's make sure, Git branch, I'm on master, let's push it. Git push. I'm on branch master, so I don't need to specify that. I just need to specify the target. I'm pushing to my origin on GitHub. I have several branches there. I'd like to push to the master branch there, for example. Not an excellent practice for programmers. We're not pushing to the master branch in RMG, for example, and any other software development scheme. We'll push to a different branch and make a pull request. Let's push it. That's all done, and we can see our repository online. Here it is. Now it has many other files, and if you look at input file, it will even have that FFCM. We can look at the commit and see even our commit that fits the merge conflict and exactly what we changed there.